Hello everyone, thanks for attending to the IEEE International Conference on Flexible and Printable Sensors and Systems. My name is Leonardo Garcia. I'm Research Fellow at the Sensor Technology Research Center at the University of Sussex in Brighton, United Kingdom, and I'm going to talk today about the development of soft gel-free ECG electrodes based on biocompatible coconut oil and carbon black. This is the outline I'm going to talk today. I'm going to discuss the motivation, the sensors, and the steps that we took to fabricate the electrodes, also the electronic readout circuit that we use to determine the feasibility of the sensors, also the ECGs measurements that we took with the electrodes compared with some commercial gel electrodes. And as the idea is that these electrodes can be used for long-term monitoring, we also carry out some strain tests to determine if they will be feasible to use them for activity and also what is the patients are in rest. And about the conclusion of this work. Yeah. Well, the motivation was to develop electrodes for long-term ECG monitoring. Electrocardiograms are usually used to determine the heart condition and also for identification individuals as this expresses unique cardiac features. These monitorings can be short or long. They can be more than 24 hours, more than 48 hours, which are called long-term monitoring. And sometimes this long exposure to the electrodes can cause skin irritations or electrodes failure as they then tend to dry. Also, these ECG monitoring are measured on the skin surface, and this can be while resting, exercise, or hotter monitoring, which is more than 24 hours. This has changed as now the increase in remote monitoring systems or telemedicine, and this implies that people are interested in monitoring some biosignals for long term. That's why we decided to develop some electrodes that can be used for this long term and physically active monitoring. But also we are interested in developing biocompatible materials that do not cause secondary effects such as skin irritation. For the fabrication of these sensors, we test two different concentrations of we use carbon black and EcoFlex in two different concentrations. We use 7.5% of total weight and 10.5% of total weight of carbon black particles. The first step was to melt coconut oil at 37 degrees. Then we add the carbon black particles and stir for half an hour to create a homogeneous dispersion. Then we add the EcoFlex part B and stir for 5 hours to create a more homogeneous dispersion using both materials. Then afterwards, we use the part B, we add the part A of the EcoFlex and stir for 15 minutes, after which we degas so to remove all the air trap in the solution. Then we just prepare the mold, a 3D printed mold with the bottom part of a snap button there. So we pour the solution on the mold and we let it dry for 24 hours. After 24 hours, we add the upper part of the snap button. We decided to use a snap button because it's the most common interface between the leads used for ECG. And other leads use this kind of connection to the electrodes. The interesting part is that when we add the upper part of the snap button, we created a suction cup shape that enhances adhesion by negative fluid pressure, which creates a small amount of vacuum and adheres to the surface of the skin, making the measurement better as the sensor is fixed and only a small amount of adhesion pad is required. Another interesting feature of this material is that it's porous and is filled with oily carbon black and coconut oil suspension. And this is also found on the surface of the electrodes, which increases the intrinsic resistivity, and which was obtained as an average of 33.2 ohms per meter in the case of the 10.5% of weight. For the ECG measurement, we use a ADS 1292R ECG respiratory breakout board with a half a giga ohm input impedance with a sampling rate of 125 Hertz. This board was connected to an Arduino Uno and then connected to a PC to get the data. To measure the ECG, we use the Eindhoven 3-lead test, 3 leads on chest configuration. This configuration is commonly used to record the potential between both arms and between the left leg and each arm. Measure the differential reading with respect to a neutral point, the left leg. But in this case, this configuration was used in the chest, as is demonstrated in the diagram here. The results, as you can see, we had better results for a higher percentage of particles in the solution with an amplitude around 0.8 millivolts, similar to the gel electrodes, and the difference of signal to noise ratio on 10.1 for the coconut oil and the carbon black, and 15.68 for the gel, having a clearly reduced noise to noise ratio for the gel one, for the commercial one. It's worth to point out that this is using the system for the ECG acquisition. Afterwards, we perform a strain test to determine the feasibility in active monitoring. Firstly, we carry out the maximum strain test till breaking point, and the maximum strain that this electrode will stand is 1,500% at breaking point. Therefore, we decided to carry on a cyclic test at 100%. So the test was done for 600 cycles at 100% for each of the electrodes, for the 3 electrodes used to measure. And it's worth to mention here that in the upper part, at 0% strain, so there was just a representative increase of 0.15%, and the average resistance at 0% strain is 7.26 kilo ohms, while at 100% the strain was 3 times the value of the initial resistance after 600 cycles. Afterwards, after this cyclic test, we performed more ECG measurements to identify what was the changes in the signal to noise ratio. And as we can see, we saw a high increase in the amplitude of the signal, and also an increase on the signal to noise ratio to minus 9.5 decibels. With this test, we have proved the feasibility in demonstrated the potential use of coconut oil as a carrier fluid for the fabrication of biocompatible and eco-friendly electrodes. And it's important to mention that we use coconut oil, but the coconut oil, it has low possibility of skin irritation, and this is an element that is widely used in the food industry and cosmetic industry. Also, it's worth to mention that we produce these ones in an expensive process fabrication that can be carried out in any laboratory, and the most important part is that the electrodes remain functional after 600 cycles at 100%. An interesting part is that also we use the same device, the same board to measure to compare the ECG of the gel electrodes, commercial electrodes, with the developed electrode to see the difference. But also we can use another ECG acquisition circuit board so we can improve the signal acquired with these electrodes. Thank you. If you have any questions, feel free. Thanks.